Good evening, everybody.
Good evening. You won't hear everybody.
Wonderful response, yes. The riotous applause I can hear from this distance already.
Yeah.
So this is a talk about seconds. As you can see, I'm going to answer 3 questions there. What is a second? What can happen in 1 second? And why do we need leap seconds? And just for your information, this talk will last about 2,000 seconds. Okay? I'm going to start with a number. Once I remember that the way this works is to click before the keyboard is responding. Okay, here's a number. 7,257,600 seconds. I'll give you just a little while to think about what is the relevance of 7,257,600 seconds. It's a particular length of time. You don't often think of seconds being written quite like this, but I'm not going to wait for a response because I'm not going to get any verbal response from you. But this is the length of time that the UK has been in lockdown. So this is 84 days in seconds. So you've been, just about everybody in the country has been in lockdown for 7 million seconds. Whether it seems like more than 7 million seconds or less than 7 million seconds, that gives you an idea of how long a second is. Of course, that's a perception rather than an absolute definition. But I thought that puts it a little bit in perspective. What I'm going to be talking about is a little bit about how we define time and motion, how seconds are defined. I'll say a little bit for context on what can happen in 1 second. And the main part of the talk is talking about how the Earth's rotation is slowing down. So I'll say why the Earth is slowing down, and I'll talk about the consequences. If the Earth is slowing down, does that mean a second is getting longer as time goes by? And I'll finish with the idea of leap seconds and the future of leap seconds. Okay, time and motion. How do we think about time? Well, time is always measured by the motion of something. Perhaps we have the impression that time is something completely different from space, but actually we always think about things moving, usually through space, to actually define time for us. And as astronomers, we all know that for many millennia, the passage of time was measured by the movement of astronomical objects. For instance, the sun moving across the sky. With a sundial, we can actually measure time by measuring the motion of the sun through the sky using its shadow. Alternatively, we can use the phases of the moon as the moon goes around the Earth. We can monitor the changing phases of the moon, and we get an idea of how time is moving over the course of a month. But if we think about what is a second, well, surely that's trivial, isn't it? The Earth spins on its axis, we know, once a day. And we know that a day is divided into 24 hours, and 1 hour is 60 minutes, and 1 minute is 60 seconds. So that means 1 second is simply that fraction of a day, 1 over 24 times 60 times 60, or 1 over 86,400. That fraction of 1 day is what a second is. That number, 86,400, will crop up once or twice, so make a note of it. So that's a second. It's that fraction of a day. Simples. So is that the end of the talk? You wish. No, there's more to it. Let's have a look at how the Earth actually moves. Now, the Earth moves around the sun in an ellipse, and that means that the Earth's speed around its orbit is not the same everywhere. The Earth's speed varies depending on its distance from the sun. And if my cursor is working, you can see that on the left-hand side, the Earth moves quite a lot in 1 month when it's close to the sun, but on the right-hand side, the Earth moves a relatively small distance in that same time period of 1 month when the Earth is at its furthest point from the sun. So the speed of the Earth around the sun, around the sun in its elliptical orbit changes during the year. And that's one of the reasons, that's the main reason why sundials don't read correctly, because the Earth is traveling at different speeds, and so the sun does not appear to be in the same point in the sky at the same time of day. In fact, if we actually photograph the sun at the same time of day, doesn't have to be noon, but in this particular case, here's a picture of the sun photographed at noon throughout the year, we find that the sun varies in terms of its altitude above the horizon, and there's clearly an east-west variation as well. So the north-south variation is a result of the 23-degree tilt of the Earth's axis. In the northern hemisphere, we know the sun is higher in the sky in summer and lower in the sky in winter. This particular picture was taken in the northern hemisphere. So we know that the lowest point of the sun was December and the highest point was June. But the point of this analemma is to show you that as well as having a north-south variation, there is clearly a variation in east-west, even though it was taken at the same time of day. Sometimes the sun is a little bit east of the meridian at noon, sometimes the sun is a little bit west of the meridian at noon, and that's because of the elliptical orbit of the Earth around the sun. It's nothing to do with the speed at which the Earth is rotating on its axis. So the analemma tells us that sundials can't be used to tell us how fast the Earth is rotating. The variation we see, the fact that sundials never accurately measure the time of day, is not because of the Earth's rotation on its axis, it's because of the way the Earth moves in an elliptical orbit around the sun. So if we wanted to measure variations in the length of the day, then we need a clock that's much more accurate than a sundial. And for the rest of this talk, when I talk about the length of the day, I'm talking about the rotation period of the Earth. I'm not talking about daylight, the period in between sunrise and sunset. I'm talking about the nominal 24-hour rotation period of the Earth. So we need something better than a sundial if we're going to measure this. So coming back to the question, what is a second? Defining it as a certain fraction of the day doesn't help. Since 1968, the second has had a very precise definition. It is that many oscillations of the cesium atom, or if you want to be technical, it's that many oscillations of the microwave radiation corresponding to a transition between two energy levels of a particular isotope of cesium that just happens to be called cesium-133. That doesn't really matter so much. But since the 1960s, people have been building clocks, and it doesn't look like it, but the picture in the bottom right is a clock that is measuring time by looking at the radiation produced by cesium atoms. Cesium atoms were chosen for a number of different reasons, one of which is that the cesium-133 isotope is extremely stable. And measuring time according to that many oscillations of the cesium atom is called the cesium standard. And it's been with us for more than 50 years now. So the device in the picture there might look a little bit cumbersome, but given its accuracy, it's actually a relatively compact clock. The radiation, the cesium radiation, allows us to measure the passage of time to a precision of better than 1/billionth of a second, 1 nanosecond per day. Or if you prefer, how long until it starts drifting out by 1 second? Well, it would drift by about 1 second in 30 million years. And the advantage of atomic clocks is that every atomic clock you build, as long as you build them correctly, will all keep time with each other. In other words, a cesium atom in England behaves exactly the same way as a cesium atom in New York or Japan or Australia or anywhere else. And hence we can have something close to a universal time. NASA have developed a relatively compact clock, which they're calling the Deep Space Atomic Clock. It's about the size of a toaster. It's this object on the top of this particular space probe. I'm not sure which probe is being shown here, but the atomic clock is this box on the top of the right-hand picture. And NASA have developed this atomic clock to put into space probes to improve navigational accuracy. In other words, if you've got a space probe traveling very fast through the solar system, the more accurately you know the time, then the more accurately you know where you are. The probe can, to some extent, tell where it is by monitoring its own acceleration, and as long as it knows the time accurately, it can work out how fast it's traveled in a given time. So that's something that NASA are developing and will be in future space probes within the solar system. Time definitely matters, because if we think of other atomic clocks, for instance, the atomic clocks that are in the global positioning system, the GPS satellites, there's an indication in the graphic on the right of how it works. We're trying to work out our position on the surface of the Earth, and we do that by looking at signals from various satellites that are above our horizon at any given time. And it's the time difference between when the satellite sends the signal and when they're received on the Earth's surface that determines our position on the Earth. So all of the atomic clocks have to be synchronized, and we have to know, to work out our position, we have to know the time differences between the time a signal is sent and the time it's received on Earth. So you can perhaps see that given that we know the speed of light, if the clocks are wrong, for instance, if a clock is wrong by 1 millisecond, 1/1000th of a second, then the distance that signal would travel would be wrong by 300 kilometers. And if we had a GPS system that wasn't accurate to within 300 kilometers, we would pretty much know which continent we're on, but not necessarily which country. If the clock was wrong by 1 microsecond, so now we're down to a millionth of a second, the distance would still be wrong by about 300 meters. Good enough to get you across the Atlantic if you're navigating in a ship, not so good if you're trying to work out when the next left turn should be off a road, for instance. So yes, accuracy matters. We have to keep these clocks very closely synchronized if we want GPS to give us a position accurate to within, let's say, a meter or two. And because of that, the GPS clocks are resynchronized quite regularly. Although in principle, the clocks can be left alone for quite a long time, they are, wherever possible, resynchronized with master clocks on the ground every few hours to make sure that all the clocks agree with each other to keep the GPS system accurate. So what can happen in 1 second? Well, let me just give you a little bit of context to give you an idea of just how long a second is. If you've been in lockdown for 7 million seconds, you may not think they're particularly long, but let's have a look. Let's have a think about what a computer can do. This picture on the left-hand side is an IBM computer. It's one of the fastest supercomputers in the world. It's sitting in the Oak Ridge National Laboratory in America. And the number above it is 200,000 million or 200 billion. That's not actually the number of calculations it can do in a second, because I missed some zeros out. There's a few extra zeros. That's still not enough. There's a few more. That is the number of calculations that this computer can do in 1 second. 200,000 million calculations. That is pretty damn fast. And bear in mind, when anybody shows you something like, here's a simulation of what the early universe looked like, or here's a calculation of where we think the dark matter is in this supercluster. These enormous simulations are carried out on supercomputers like this, and even with that sort of speed, running a simulation of, for instance, the evolution of the universe could take days or weeks or months of number crunching time. So you can see at 200,000 million calculations per second, a calculation might still take a few months. So you get an idea of the complexity of some of these calculations that are done in astrophysics. But still, it's a mind-boggling number in terms of trying to work out just how anything can do that many calculations in 1 second. We know about the speed of light. We're astronomers, so we know the speed of light is fairly high. When I was a lad, the speed of light was 186,000 miles per second. It's now 300,000 kilometers per second, which is, I hope, the same number. They've just changed the units on me. And we know that is pretty fast. We know the moon is 1 light second away, and we all have a rough idea of what's meant by a light year, even though it's an incomprehensibly large distance because light travels so far in 1 second. If we think of man-made objects, two of the fastest man-made objects are the Voyager planetary probes, and they're traveling at the moment at about 16 kilometers per second. They're both leaving the solar system via different routes, and they're both traveling at roughly the same speed, the escape speed of the solar system, 16 kilometers a second. Quite pedestrian compared to the speed of light. Though if you imagine some distance that's 16 kilometers away from you, and then imagine an object covering that distance in 1 second, you get an idea of the speed of the Voyager probes. But that's a little bit esoteric in that none of us own a Voyager and none of us can hope to travel at that sort of speed. But there's a way of getting an idea of just how long 1 second is if you think of it in terms of something a little bit more mundane, and that is what happens on Earth in 1 second. And I've picked a particular set of examples taken from statistics from 2019 in terms of what happens on the internet. So in 1 second of last year, 300,000 text messages were sent, 300,000 texts per second. And in terms of internet searches, there were something like 60,000 searches per second from either Google or, of course, other search engines are available. What else was happening in 1 second of last year? Well, 75,000 videos were streamed every second last year. I think at least half of them involved cats, but I'm not too sure about that, but certainly there were an awful lot of them. 700,000 messages such as WhatsApp and things like that were sent. And one of the most staggering numbers I found from last year, and it will almost certainly be higher this year, the total number of emails sent was approximately 3 million emails per second. And that was for every second of last year, and I'm sure it's even higher this year. So in that sense, an awful lot can happen in 1 second. And that is really the domestic use of the internet. That doesn't include scientific use. It doesn't necessarily include financial use of transactions going across the globe. These are just what most people will be using their phone or iPad or laptops for most of the time. So if we actually use atomic clocks, which have been going for 50 years now, we can tell that the Earth is slowing down. We don't seem to feel things any differently, and it still seems to be turning roughly once every 24 hours. But because atomic clocks are so accurate, and because atomic clocks will only drift by 1 second over 30 million years, because we've been monitoring the rotation of the Earth for the last 50 years, we know that it's slowing down. Back in 1968, when atomic time was instigated on the Earth, it was designed such that the definition of the second was such that the Earth turned in 24 hours, 0 minutes, 0 seconds. In other words, the Earth turned once in 86,400 seconds relative to the Sun. But over the last 50 years, things have changed. Although it was exactly 24 hours, we now find that the Earth turns in 86,400.001 seconds. The Earth has slowed down in 50 years by 1 millisecond, 1,000th of a second. And as far as we can tell, it's been doing that for a long time. Where did it all start? Well, technically it started when the Earth formed, but something like 4.5 billion years ago, the Earth was hit by an object which is often called Theia, which is a sort of Mars-sized object that clouted the Earth and produced a whole large amount of spall, which eventually became the Moon. And the Earth might have rotated at who knows what speed before this collision, but the Theia impact would have changed the Earth's rotation. And it took the Earth a little bit of time to recover from such a massive impact as that. But it is thought that as soon as the Earth recovered from the Theia impact, it was rotating with a period of about 5 hours. Somewhere a little bit less than 6 hours is the current thinking for the rotation of the Earth. So 1 day used to be 5 hours in current terminology, and the Earth has been slowing ever since Theia impacted the Earth. So over those 4.5 billion years, why has the Earth been slowing down? It's because of the Moon, which was generated at the same time. So here we can see that the Moon generates tides, and here's the tidal bulge on the near side, the side closest to the Moon. There's also a bulge on the opposite side, but let's just think about the bulge that's closest to the Moon. The Moon will be pulling on that bulge, and the bulge, you notice, is not in a straight line between the center of the Earth and the center of the Moon, because the Earth is rotating and it tends to pull that bulge a little bit offset from the line joining the Earth to the Moon. And that means that when the Earth pulls on that bulge of water, it tends to slow the Earth down because it's tending the Earth wants to rotate in an anti-clockwise sense, as seen from above the North Pole, and the Moon is tugging on this bulge of water and trying to slow it down. So over the last 4.5 billion years, the Moon has slowly been slowing the Earth down. In exchange, the Earth has been pushing the Moon into a higher and higher orbit. So what that means is, well, you could say, so what? The moon has been slowing the Earth down. It used to be a 5-hour day. It's now a 24-ish hour day. So what? The day is not an exact number of seconds anymore. It used to be 86,400. It's now 86,400 and a bit. So who cares that they're not quite the same? Well, it's just like the problem we have the year being not an exact number of days. So everybody, I think, is aware of the fact that a year is not 365 days. It's not actually 365 and a quarter. It's a little bit less than 365 and a quarter days. If that wasn't addressed and we only had 365 days in our calendar year, that means the calendar would very slowly, year by year, drift out of sync with the seasons. And instead of having a northern summer in July, we would have a northern summer in December, for instance. So we can get around that problem by inserting an extra day every 4th year, and that makes the calendar year 365.25 days, 365 and a quarter, if we add a leap day every 4th year. And of course, that gets it almost right. We're trying to make the year 365.24 and a bit. So 365.25 is not quite right. And it was realized some time ago that if we simply skip over a leap year in a century that's not divisible by 400, that makes the calendar year 365.2425. It's a roughly 365 and a quarter, and taking away 3 out of every 4 century leap years gives us a very accurate way of keeping the calendar in sync with the seasons. So that is pretty close, and that's why we have a leap year. And the formula, let's put one in every 4th year, unless it's a century not divisible by 400. That's a formula which will keep us going for thousands of years. If we kept on with that particular formula, we wouldn't have to adjust the calendar for thousands of thousands of thousands of years. It's a very neat way of dealing with the fact that a year is not an exact number of days. So we can ask the same question about the rotation of the Earth. If we want our 24-hour clock to stay synchronized with the rotation of the Earth, if the Earth is rotating in a period that is not quite 24 hours, then we would have a drift and the sun would not be in the sky when our clocks say it's daytime, unless we keep making adjustments to keep our 24-hour clock in sync with the rotation of the Earth. And so just like we add leap days to do that for the calendar, we can do that by adding leap seconds every once in a while to keep the Earth's clocks in sync with the Earth's rotation. So that's the general idea. Actually, we don't have to do that, and that's part of the controversy of leap seconds. We don't have to add a leap second every once in a while. We can say, well, we don't want our clocks to get out of sync with the rotation of the Earth, and maybe we don't want to add leap seconds either. So we could just say, well, the Earth rotates in 24 hours, and therefore, if the Earth starts slowing down, that means an hour starts getting slightly longer. A minute gets slightly longer. A second gets slightly longer. If we simply run our clock slow, then we would be okay. We could keep the clock synchronized with the rotation of the Earth if the Earth is slowing down, simply by letting our clocks slow down. And that is an alternative. However, scientists would be furious if we allowed that to happen, because scientists have spent a long time defining the second very precisely, such that we have an absolute standard by which we can time other natural phenomena. If we suddenly say, no, we're going to have to redefine the second because we know the Earth is slowing down in the long term, could be speeding up in the short term, we're going to have to keep readjusting our definition of a second to keep tabs on what the Earth is doing. In other words, atomic clocks would have to be set to run on average at slower and slower and slower rates in order to keep up with the changing speed of the Earth's rotation. The definition of the second would change every day, every hour, essentially every minute, every second. The definition of a second would have to keep changing. And scientists effectively digging their heels in and saying, no, we don't want to allow that. We want seconds to be absolutely fixed. Therefore, if the Earth is slowing down, well, I guess we'll just have to add leap seconds every once in a while. And the every once in a while is part of the problem. Here's a diagram, I'll talk you through it. This is a graph showing the length of a day minus 86,400 seconds. In other words, it's the extra bit that we're talking about. The length of a day is 24 hours plus a little bit, and this graph is showing you what that little bit is. The vertical scale goes from 0 to 5 milliseconds, and you can see that there's been a lot of variation over the time period from the 1960s up to almost the present day on the right-hand side there. So you can see it looks like a very noisy variation. It sometimes goes up, sometimes goes down, and it seems to be jigging up and down all over the place. So if we have a look at that variation, if you look closely and compare it with the date scale, you can see that year on year, it goes up and down every year, up and down every year, up and down every year. Not always by the same amount, but there's always an annual variation in the speed at which the Earth rotates. That is understood. That is a consequence of what the Earth's atmosphere is doing. During the summer, during northern summer, more of the sun's light hits the northern hemisphere, and that warms the northern hemisphere up more than the southern hemisphere. And conversely, in northern winter, more of the sun's light is hitting the southern hemisphere. And as a result, the circulation of air around the Earth changes between the seasons, between spring, summer, autumn, and winter, regardless of which hemisphere you're talking about. The circulation of the Earth's atmosphere changes. And in some cases, there are very strong atmospheric circulations running from east to west, and sometimes they're from west to east. And those patterns change year on year. And because the Earth's atmosphere is actually dragging effectively against the Earth, that affects the speed at which the Earth rotates. So that's why we see this speeding up and slowing down of the Earth on a yearly basis. Perhaps you can also see, if I move the mouse, there's some wiggling, not only the big variation that I've just talked about, there's some variation in terms of small wiggles on a scale of maybe a few months and maybe a few years. These are probably the results of earthquakes. If the solid mass of the Earth changes because a continent changes position by a few meters, either goes up or goes down or goes sideways because an earthquake makes the continental plates shift, then that change in the Earth, the crust of the Earth, can actually make the Earth spin change by a fraction of a millisecond. But as well as that, the elephant in the room is this big variation we can see. If you look back in the 1960s, the rotation period of the Earth was 24 hours plus a millisecond or two. And then during the 1970s, it went up to an extra 3 milliseconds for the length of the day. Then it came down again, then it went up again, then it came down again. And at the moment, well, 2020, I'm not sure quite what it's doing. I think the Earth might be speeding up a little bit. What I find really curious is that this variation over the last few decades where we've been able to measure it, prior to this, we didn't have clocks accurate enough to measure this sort of variation. The reason for why the Earth gets faster and slower by a few milliseconds over a few decades, I'm very surprised to learn that people don't really understand what's going on there. It's not the atmosphere that's responsible for the spiky annual variation. It's not the crust changing, because we can see the effect in the fainter red line, for instance, that we see varying over a period of months or years. So what is it? Is it something inside the Earth? Is there something inside the Earth? Is it part of the liquid core or mantle that's changing and actually changing the rotation period of the Earth? I'm rather interested to realize that geologists don't understand exactly why that is. So there's still research to be done on understanding even our own planet, let alone planets in our solar system. So what about leap seconds? We know about leap days. If we need a leap day every 4th year, we know exactly when it's going to happen. A leap day is going to be inserted on the 29th of February, and we know exactly which year a leap day is going to be inserted. We know what that's going to be. For the next 1,000 years, we could write down which year is a leap year, and therefore we know a leap day is going to be inserted on the 29th of February in a given year. But leap seconds are not the same. Remember that graph we just looked at? There are variations there we don't understand. So with the Earth going around the Sun, we know that's 365 and a quarter, maybe a little bit less of a day. We can predict what's going to happen hundreds, thousands of years into the future. But with leap seconds, we don't know exactly how the Earth is going to behave. So how are we going to decide how to put a leap second into our clocks? Well, that decision is made by an organization called the International Earth Rotation Service. Yes, I kid you not, there is such a thing. How we made sure the Earth rotated properly before this service existed, I don't know. And exactly what happens if they decide to take the day off, again, I don't know. But this organization is responsible for deciding how often a leap second should be added and when the leap second should be inserted into the day and into the month. So if we go back to that picture, you can see it's apparently quite erratic, but I'm not looking now at the Earth rotation period. I'm looking at this fainter grey line. In 1972, that's the point at which leap seconds were introduced. And they were introduced according to that particular pattern. So now we're looking at the axis on the right-hand side that tells us we've had 27 leap seconds introduced since leap seconds started back in the early 1970s. And if you compare that with the grey graph in the background, you notice that in the 1970s, when the Earth's rotation was 24 hours plus quite a large 3 milliseconds, that the day was quite a long way away from 24 hours, and it was necessary to put quite a few leap seconds in. Effectively, we were adding a leap second approximately every year. But notice what's happening in the early part of the noughties. Between 2000 and 2005, for some reason, the Earth sped up. And again, I don't think we really understand why that is. But between 2000 and 2005, the Earth sped up for a little while, and its rotation period was very nearly 24 hours. And that's why very few leap seconds were added between 2000 and 2005. For quite a while, the Earth Rotation Service decided the Earth's rotation period is close enough to 24 hours that we don't need to add any more leap seconds. But since then, the Earth's rotation period has changed again, and a few leap seconds have been added. The last leap second that was added was in 2016. And it has to be decided when the next one is going to be. It is not going to be in June of this year. They usually add a leap second in June or December of a given year. It has been decided that they will not introduce one in June of this year. They may introduce one in December of this year. The decision has not yet been made. But you can see the reason for the concern is the fact that we don't know quite what the Earth is going to do in the next 12 months. It seems almost chaotic. So we can understand some of the variation, but if we don't understand what's producing these milliseconds of variation, then we can't predict what the Earth's rotation is going to be in a few years' time. So we can't tell how many leap seconds we're going to have to introduce. And that annoys an awful lot of people, because some people rely on accurate timing and knowing what the time of day is. So if you don't know whether a leap second is going to be introduced in a few months' time, it's very difficult to make sure everybody's clocks are always synchronized. If you decided to add a leap second, for instance, at midnight, you know what a clock normally looks like. If you look at the bottom right hand of this picture, a clock going through midnight normally looks like this. It gets to 59 and then it changes to 0. But if a leap second is introduced at midnight, what happens is, as the clock approaches midnight, an extra second is introduced. So a minute actually has 61 seconds. So if anybody ever asks you how many seconds are there in a minute, the answer is not 60. The answer is usually 60, but every once in a while, a minute might contain 61 seconds. And you can see from that picture where it's got the time 23:59:60, that is a perfectly legal and valid way of expressing the time if there is a leap year added. But that's part of the problem. Some computers don't actually realize that. So you can get a problem. When should you insert a leap second? Should you do it at local midnight when nobody gives a damn? Well, midnight where? If you decide that it should go in at local midnight, that means the UK will put it in at a particular time of day, but America would insert their leap second at midnight quite a few hours later. And of course, Japan and Australia would be inserting their leap second quite a few hours earlier. And you cannot have that. In these days of global electronic finance, you cannot have clocks out of sync with each other across the world. If you want to move $1 billion from one country to another, you can't have any ambiguity of what time it is that you're talking about. Is it the time according to our clocks or your clocks? And have you added the leap second yet, or have you not added the leap second yet? It's absolutely vital that everybody's clocks stay completely synchronized. And that is what is getting people so concerned. Some people really don't like leap seconds because of the uncertainty of when the next leap second is going to be inserted. And also, you have to keep a very careful record of when all the previous leap seconds were inserted if you want to go back in time and work out what happened at a particular point according to somebody's clock. You've got to know how many leap seconds were added to their clock in the past. And some computer systems really don't like leap seconds, to the point where some computer systems will actually crash if you try and put in a leap second time, even though in principle they shouldn't, because it's a perfectly legal thing to do. And that's why some companies don't really like leap seconds either. For instance, Google have said we are not going to insert an extra second into one of the minutes during a day that's got a leap second added. We're not going to wait until the last minute, or indeed we're not going to have any particular minute in the day have 61 seconds. That produces a glitch, it produces an anomaly, and it makes all the clocks glitch. So Google have said we are going to smear the leap second and not insert it at one point in the day and have a minute having 61 seconds. We're going to add the leap second drip feed. We're going to add it a few microseconds at a time continuously throughout the entire day. In other words, we're going to run our clocks slow. We're going to run our clock slow such that by the end of the day, the clock is running 1 second slow, and therefore the day will have 1 extra second in it. But none of the minutes during that day will have 61 seconds. Google have decided to do something different from everybody else in order not to have a 61-second minute. Well, that's sort of okay, but nobody else does that, which means Google clocks during a day of a leap second are technically out of sync with everybody else's clocks in the world. Now, it's sort of okay because you probably won't notice if a clock is running 0.001% slow. That's all you need to make up 1 second in one day. But as a joke, somebody once said, well, imagine if you did the same thing, not for a leap second. What if you imagine doing that with a leap day? Hence this particular cartoon, in which one person says, why are the clocks saying it's 3 a.m.? And the answer is, well, adding an extra day, a leap day on February the 29th, causes too many glitches. Instead, we're running our clocks 3% slow during February, and then we won't have any glitches. So that's the joke, that Google has expanded their leap second smearing to cover leap days as well. So that shows you the absurdity of trying to do smearing, but Google are sticking to their guns, and that's what they're going to do. So leap day smearing is a joke. But the problem of leap seconds is quite serious. The Earth is slowing down on average, sometimes slowing up. So if you want to keep your clock synchronized, do you make seconds longer and irritate all the scientists? Or do you add a leap second and you have to add the leap seconds at times which are difficult to predict and you can't easily work out what's going to happen other than a few months ahead. That is the controversy over leap seconds. There's a so-called International Telecommunication Union, otherwise called the ITU. It's a United Nations agency that has considered whether or not time signals should continue to have leap seconds inserted. We've had leap seconds since 1972, and we've had 27 of them in the last 50 or so years. And the question is, should we continue to have leap seconds when there's all these problems in globally trying to keep clocks synchronized? And when you're moving large amounts of money around the world, every millisecond counts. So you can't afford to have clocks out of sync. So they had to consider what to do about leap seconds. Do you annoy the scientists, or do you just let the clock drift relative to the rising and setting of the sun? Well, in 2015, they came to a decision. They thought long and hard about this, and they made a monumental decision in 2015. And they decided not to decide until 2023. They simply put it off, and they're procrastinating. Somebody somewhere is going to have to decide what we do about leap seconds, and we've got a few years to sort it out. Appease the scientists, let the clocks drift, or continue with leap seconds. None of those is entirely satisfactory, but you've got to do one of the three. So perhaps in the next 3 years or so, somebody somewhere will make a decision. So thank you for your attention for the last 2,000 seconds. I've been telling you about what a second is, what can happen in 1 second, and why the slowing of the Earth's rotation has the consequence that we possibly need leap seconds. Thank you all very much.
Thank you, Steve.